Hi everyone, I'm Zhiming Li, a PhD student from Nanyang Technological University. My work to present today is cross-lingual transfer learning for statistical type inference. Deep learning-based techniques has been widely applied to program analysis tasks in fields such as type inference, vulnerability detection, and code summarization, etc. Present deep learning-based software engineering systems mostly rely on supervised learning approaches. The supervised learning paradigm is shown in the slide. For example, if we were to build a neural vulnerability detection system for JavaScript, first, we collect a large unlabeled JavaScript dataset, and given the unlabeled dataset, in order to train the neural network model for prediction, we have to label a significant amount of samples in the dataset in order to make the data-hungry neural model works. Unlike other domains like computer vision and natural language processing, the labeling process is much more harder and non-trivial for programming language since it requires considerable domain knowledge. Hence, it will be extremely valuable if we are able to learn new models for new languages based on existing labeled data of another, avoiding the need to invest additional efforts in labeling. In this case, it would save us a lot of effort if we can leverage existing labeled Java or Python vulnerability detection dataset to train the neural model for JavaScript. To achieve this goal, we introduced a general cross-lingual transfer learning framework, Plato, for program analysis tasks based on BERT model. Our key insight is to exploit common features of different programming languages relevant to the analysis task and to reduce the impact of irrelevant features in order to make the best use of existing labeled data from other languages. The overview of Plato is shown in the slide. Specifically, given the labeled in-domain source language data and out-domain unlabeled target language domain data, we first perform syntactic and data flow analysis to get a source code, source ML syntactic tagging parallel dataset, as well as a novel code graph, which we called variable relation measurement, for all the samples in the language corpus. They are used as the input for downstream supervised training of the backbone model. After training on the source language domain in a supervised manner, we synergistically combine the kernelized model and the original unkernelized model for inference on target language using a bagging-based inference ensemble strategy. We introduce the details of these proposed components in the following. The details of the model architecture is shown here, which contains two major components, syntax enhancement and kernelized attention. They aims to increase cross-lingual feature overlap and decrease cross-lingual feature difference respectively. First, for syntax enhancement, in order to preserve more structural invariant among different programming language domains, we enhance the original source code representation with meta-syntactic information such that the model can explicitly leverage the overlapped information for prediction. In this work, we use source ML meta-language tagging, which is as shown in the slide. At a high level, source ML meta-grammar provides each token in a code sequence with the corresponding markup tag that represents the abstract syntax row of the token, which is unified among languages. Concretely, given a code sequence and its corresponding source ML sequence, we map them to their respective embedding. Then, the augmented input representation is the weighted sum of the source code token embedding and the source ML token embedding. Second, we introduced the kernelized attention mechanism. For traditional attention mechanism, the embedding of a word depends on its relation with all the other words in an input sequence. In other words, there is no constraints to attention scope during gradient-based learning. For example, consider a code sequence as shown in the slide. When calculating embedding for token A, the traditional attention takes all the other tokens in the input sequence into consideration. Yet, when performing type inference for A, the declaration statement of B is irrelevant and should not be considered when making the prediction. On the other hand, if the prediction is erroneously based on B or 0, the model would not be transferable or generalizable. To mitigate this concern, we propose a kernelized attention mechanism, which uses the shortest path graph kernel based on a novel type closeness graph to constrain the attention scope of tokens in code sequence. In this way, given a query token, the model tends to use the set of tokens that are more relevant. In other words, the closest token in the graph for prediction. Figure 1 shows the type closeness graph of a sample code. Concisely, the graph is constructed based on the abstract syntax tree and is augmented with edges retrieved from reaching definition analysis, which are denoted as dashed arrows in the figure. Then, given the type closeness graph, we can now obtain the variable type closeness adjacency matrix based on the type closeness distance as shown in figure 2. Specifically, the distance of two nodes in the graph kernel space is the minimum of their lowest common ancestor distance and the reaching definition analysis edge distance. Finally, after obtaining the adjacency matrix A, we constrain the BERT model attention by taking element-wise multiplication of the attention vector with a regulatory weight vector G sigma A, where G sigma is the radial basis function. Intuitively, the more distance two tokens are in the graph kernel space, the smaller their regulatory weight is. In this way, the model is constrained from using tokens that are relevant for embedding. Finally, by taking dot product with the sequence embedding C, we obtain the kernelized attention embedding. In this way, we expect the model to learn a feature about variable relationships, therefore decrease the counter effect of the irrelevant or noisy features which hinder the transferability of the model. We apply the kernelized attention mechanism at both the pre-training stage and the fine-tuning stage. While the kernelized model is able to use explicit syntactic and semantic relationships to improve the performance of type inference, it may fail to cover some corner cases. For example, for variable within assignment statement, features within the kernelized attention scope may be language specific, thus does not generalize to other language domains and lead to negative transfer. Therefore, we use the bagging-based ensemble strategy, which combines the kernelized and unkernelized model during inference stage, such that the combined model can make the best of both worlds. We conduct experiments under 3 settings. First, we evaluate Plato under a scenario when there's no labeled target language data and aims to evaluate the transferability of type system among different languages. This is broadly regarded as the domain adaptation task for deep learning systems. Second, to simulate the real-life scenario when we don't have sufficient labeled training data, we evaluate Plato under the setting when there is only partial labeled target language data and see whether augmenting the training set with cross-lingual labeled language data is beneficial. Finally, for the last setting, we evaluate Plato under the full labeled source language data and see whether it is effective. For the first setting, we consider the overlapped built-in types among different languages, which contains Boolean, integer, list, dictionary, etc. We evaluate the domain adaptation among optionally typed and strongly typed languages. Specifically, Python to TypeScript, Java to TypeScript, TypeScript to Python, and Java to Python. We compare Plato with 3 popular domain adaptation methods, which are widely used in text and image classification tasks. Task adaptive pre-training, maximum mean discrepancy, and adversarial domain adaptation. In addition to the 3 evaluated baselines, we show the results of supervised learning on in-domain data only without any domain adaptation techniques, denoted as supervised subscript I. This can be regarded as the performance lower bound. Besides, we show the results of supervised learning on the out-domain data, denoted as supervised subscript O, which can be regarded as the performance upper bound. Table 1 shows the detailed results of different models in terms of exact match and weighted F1 score. Overall, the results demonstrate that our method significantly outperforms the 3 domain adaptation techniques in terms of all metrics, using either optionally typed language or strongly typed language as the source language data. Interestingly, the results show that Java can achieve comparative performance compared with Python or TypeScript data, which illustrate the potential of leveraging the type information of the existing strongly typed language, which is abundant and effortless to retrieve. Also, note that Plato can achieve comparative or even better performance than existing role-based type inference tools on these primitive types without much manual effort or expert knowledge, which further demonstrates the value of cross-lingual transfer learning among different programming languages. We conduct an ablation study to demonstrate the effectiveness of different components. The results are shown in Table 2. It is obvious that both the syntax enhancement and kernelized attention is effective in boosting models' performance. To better understand the source improvement of the kernelized attention, we conduct a case study as shown in Figure 1. Specifically, we visualize the final layer attention of the Boolean variable show colors for both the original sequence model and the kernelized model. For a sequence model, it's shown that models seriously leverage the irrelevant token timeout interval for prediction while completely ignores the ground truth evidence true. By incorporating kernelized attention, model robustly infers the variable as Boolean based on ground truth evidence true. The visualization shows the kernelized attention forces the model to base its inference on relevant domain invariant features, thus making it more robust and transferable among language domains. For the second and third setting, note that in the real-world scenario, during the early stage of an optionally typed programming language, the typing annotations of the language provided by developers are scarce. Thus, it will be extremely valuable if we were to quickly build a functional type inference tool by leveraging existing cross-lingual label dataset to augment the training data of the model. We selected a limited ratio of samples from the target dataset, for example, 10% or 20% of labeled target language data samples to simulate the scenario, and train the model together with the off-the-shelf label source language dataset. We compare Plato with two baselines, the vanilla BERT model trained with only a limited ratio of target language data, and Plato without kernelized attention. The results are shown in Figure 1. We can see that Plato without kernel steadily outperforms the baseline BERT model under both settings. Particularly, the improvement is more significant when the size of label data is small. Besides, we notice that Plato significantly improves over BERT and Plato without attention baselines under all ratio of labeled target data for both the intra and inter-project settings, which indicate that using our proposed kernelized attention is a bit effective in boosting models' performance for all data ratios. Finally, if we evaluate Plato with the SOTA type inference baselines, the lower two tables shows the results for both the TypeScript dataset and Python dataset under both the intra and inter-project settings. We observe that Plato can effectively improve over the baseline methods by leveraging cross-lingual data as well as the kernelized attention. In this work, we set out to conduct the first trial of cross-lingual transfer learning of statistical type inference. We propose two novel domain adaptation techniques, namely syntax enhancement and kernelized attention, which are proven effective under multiple evaluation settings. In the future work, we plan to conduct extensive evaluations of our framework on other different benchmarks such as code summarization, vulnerability detection, etc. Second, we will evaluate our framework on different network architectures like recurrent and graph neural networks. Finally, since different languages has different attributes and usage scenarios, we plan to evaluate the transferability among different languages. That's all of my presentation. Thank you for listening.